We're now going to use these general lateral trim equations to look at the problem of minimum control airspeed. And minimum control airspeed is important on all aircraft, but especially important on multi-engine aircraft. So let's look at why that is. So if I'm looking at an airplane here from the top, and this is a multi-engine aircraft, so I've got some thrust on either side. One of the failure conditions that we have to plan for is if we lose an engine during flight. And how do we've still got to be able to trim the aircraft and successfully and safely operate that aircraft. So let's look at this case of losing an engine here for just a moment. So let's say that I lose my right engine. Then I've got to offset the entire drag of the aircraft basically with the by using thrust on the left engine. And in order to do that, I will then have I'm going to have to use some rudder deflection back here, so we'll call that delta R to offset that, and we're also going to need to use some ailerons to trim this out. And so usually what we do is usually you want to bank into the operating engine and away from the engine that's out. So our operating engine will now be lower than, so we're going to bank to the left here. So that means we're going to have positive aileron deflection on the right and negative on the left. So if we were to look from the back of this aircraft, it's going to be banked to the left here to trim this out. So now we've seen that we can trim this by increasing the bank angle and messing with the side slip and the bank angle, and actually the further we bank, basically within these linear approximations, the further we bank, the less deflection is going to be required to trim this out. Well, the worst time for this to happen is actually during takeoff and landing. The reason for that is that at takeoff and landing, our dynamic pressures are low. And so the forces that you get from forces and moments that you get from your control systems are directly proportional to dynamic pressure. Dynamic pressure is directly proportional to velocity squared. And so at low velocities, we have very low forces and moments being generated by these control surfaces. And so, and at low velocities, that's when our yawing moments from a single or an engine out scenario, we're at probably full throttle here to take off. Our yawing moments can be the greatest from our propulsion system if it's asymmetric. So this becomes a very important sizing condition, this takeoff and landing condition, where we're at full throttle and we have one engine inoperative. And this basically will size. It's one of the common sizing cases for a rudder, for how large the rudder needs to be so that it could trim out this case. Okay. So at takeoff and landing, we're kind of limited on the bank angle that we can apply. The larger the bank angle within these linear approximations, the larger the bank angle, the less deflection we're going to need on our control surfaces. But we're limited because we're very near the ground. We can't bank significantly. And so a common regulation or design point is that we want to size the rudder so that we need no more than 5 degrees bank angle. So phi is less than or equal to plus or minus 5 degrees. Okay, so that's kind of a design point that you can design towards, that we need to be able to trim this out at less than 5 degrees. Okay, so let's look at how we would now compute the minimum control airspeed. So as our airspeed increases, the dynamic pressure is going to increase. And so there's going to be some velocity below which we actually can't trim the aircraft with this engine out scenario, and above which we should be able to trim the aircraft. Okay, so this case is actually, up and away when we're up at flight speeds. If we lose an engine, trimming out the aircraft is not nearly as difficult as it is in a takeoff and landing situation. Now, one thing you might be thinking, why are we thinking about landing? Because takeoff makes sense. You need full throttle to take off. But But landing, you also don't want to land below this minimum control airspeed, because if you have to abort that landing, what you're going to do is go back to full throttle to do a go around. And so, so that quickly increases the yawing moment, or this asymmetric moments and forces on the aircraft, because you got to go to full throttle to do this go around. So anyway, this whole phenomenon here, this engine out scenario, is one of the main reasons why regulatory agencies require a separate pilot's license for operating a multi-engine aircraft instead of a single-engine aircraft. Now, you can still have similar effects that happen with the single engine, but they're not nearly as pronounced as they are on multi-engine aircraft, where your asymmetric forces and moments are extreme. You know, they're very large if you lose an engine. Also, you can, if we had like 4 engines up here, what we'd want to do is we'd want to look at this analysis in the worst case scenario, and losing, usually that's the furthest out engine because it has the largest yawing moment, and it could be either the right or the left depending on the direction of rotation of those propellers. Jet engines, it's less sensitive to that, but to the direction of rotation. But if you have a propellered, you've got 4 props on this thing, then the critical engine failure could be your right or your left, just depending on the rotation of those propellers. So anyway, okay, so let's get into it and see how we can use these equations now to analyze what our minimum control airspeed would be. So we're going to start with these general equations again, and I'm just going to walk through some manipulation of those. So what we're going to do is take this stuff first and move it over to the right-hand side. And then I'm also going to invert this matrix and multiply it to the right-hand side. So we're going to do a invert to get that over to the right-hand side. And then I'm going to divide the whole thing by the weight coefficient. Okay, so I'm not going to walk through each of those steps. Let's just write down what that looks like by the time we're done here. So what we end up with is we're going to divide the right and the left-hand side by this weight coefficient. So on the left-hand side, we're going to be left with this vector here, this beta over CW, delta A over CW, and delta R over CW. And that's equal to this matrix right here that we've inverted. And I'm not going to write out all the components. It's this matrix right there. So it's the inverse of that matrix multiplied by, now I've divided this stuff here by the weight coefficient. And so what happens is I get back dimensional values for side force. So Y sub P, that's the side force from the propulsion system, divided by weight, minus the rolling moment of the propulsion system, divided by the wingspan times the weight, and the yawing moment of the propulsion system divided by wingspan and weight. And then we also have a minus phi. Now, we used to have a sine phi here. I'm using the small angle approximation because we're going to assume that we're limited to plus or minus 5 degrees, okay? So I'm just going to use a small angle approximation over there. And so this is my final set of equations now that I'm going to use to compute the minimum control airspeed. Now the stuff on the right-hand side here, I want to point out, is mostly independent of airspeed, okay? And let's just talk about that for a moment to make sure we understand. So these coefficients inside of this matrix here, these are these coefficients right here. These are our control and stability derivatives, and they can be slight functions of Reynolds number. Now at low speeds, we're usually talking about speeds very close to takeoff and landing, and so anyway, we can compute what these would be at those velocities. And they can change a little bit with Reynolds numbers as we get to higher speeds. They would change with Mach numbers. So once we get up past 0.3, then these coefficients can change significantly. Okay, as we go from 0.3 up to a Mach 1, or certainly above the speed of sound, then these coefficients can change significantly. So, but over a good chunk of our velocity range here, near our takeoff and landing speeds, these coefficients are largely independent of velocity. Secondly, our propulsion parameters here, those can also be a function of velocity, but if we compute those near our takeoff and landing speeds, then we can assume that those are nearly constant, even with small changes in velocity. And then we've got a weight here, and then phi. This is our bank angle, and of course we're going to limit that to plus or minus 5 degrees. So we'll probably just plug in a 5-degree here limit when we compute this. So everything on the right-hand side we can compute now from known quantities on the aircraft, and what we come up with is this our values for this vector over here. So this beta over CW, delta A over CW. So I'm just going to write that out here. So we're going to get a beta over CW, and we're going to get some numerical value for that once we've plugged in all of this information on the right-hand side. Delta A over CW, we'll get some value for that, and then delta R over CW, we'll get some value for that. Okay, so these are ratios of our deflection per weight coefficient, basically. Okay, and so now let's look at, we've got a value for this. Let's look at another. Actually, we can just write out what this is at our saturation point. So at our saturation point, this is when my control deflection is saturated. It's at its maximum deflection. Then this ratio I can write as delta A saturation divided by the weight coefficient, and instead of that I'm going to multiply it by 1/2 rho v squared SW over W. Okay, so that's the same as dividing it by the weight coefficient. So that's this ratio here. I've just rearranged it and plugged in my saturation value. And the velocity associated with that saturation, I'm going to call that my minimum control airspeed. So at the point where that saturates, that's our minimum control airspeed, okay? And this is equal to the value that I got over there from this. I'm just going to put an arrow here. This is equal to that delta A over CW that I computed from this expression up here, okay? Now I can rearrange this now and solve for VMC, and what I'll get is that VMC is equal to the square root of 2W times this delta A over CW that I got. I put a box around it. That's that numerical value that I got from that system of equations, divided by rho SW delta A sat, okay? So delta A sat is my maximum deflection that I can handle on that control surface. And once I've computed this value right there, and I can plug in the delta A sat, then what I can find is VMC. This is my minimum control airspeed for that aileron. And we could work through the same thing for the rudder. So VMC of the rudder is equal to the square root of 2W times delta R over CW, whatever I got for that ratio there, divided by rho SW delta R saturation, okay? So I'll get a value for each of these. I'll get a VMC for the aileron and a VMC for the rudder. So this is a minimum control speed, airspeed for the aileron, minimum control speed for the rudder. Now, let's say, for example, that I get 100 miles per hour for the rudder, and I get 80 miles per hour for the aileron. Well, in all likelihood, you're going to get two different velocities here, two different minimum control airspeeds, one for the aileron, one for the rudder. So if that's true, if the rudder can only control down to 100 and the aileron can only control down to 80, what is the actual minimum control airspeed of the aircraft? What should we tell the pilot is the minimum control airspeed of that aircraft? Well, it's going to be this larger of the two, okay? So whichever is larger is going to be the minimum control airspeed, because basically what we're saying is we cannot control the aircraft. We can't trim the aircraft out at velocities below 100 miles per hour. That's limited by the rudder. So this is a rudder limited minimum control airspeed. Most aircraft, most twin engine or multi-engine aircraft are rudder limited. Okay, sometimes you can get an aileron limited aircraft if you have a lot of dihedral in the wing, but usually these multi-engine aircraft are rudder limited, and so this becomes a sizing case for the rudder. This helps us determine the size of rudder we're going to need on the aircraft. Okay, so just a couple more things I want to point out here is that these solutions are basically inversely proportional to weight. Okay, over here. So these values will get smaller with weight, and which means that our these values here will get smaller with weight, which means that the minimum control airspeed will actually reduce with larger weight. So that means that we can control the aircraft. The heavier it is, actually, the lower speed we can go to and still control the airspeed, and still control the aircraft or trim it out. This is a little bit maybe counterintuitive, because most of the time we're trying to get rid of weight on an aircraft because that's associated with drag, so to increase the performance you usually want less weight. Well, in this case, to get a lower minimum control airspeed and less deflections, you actually want more weight. And the reason for that is because weight is offsetting through the bank angle. Weight is offsetting some of the control required for this, and so we're limited to plus or minus 5 degrees usually for this design. So the heavier the aircraft is, the more offset you actually get for that 5-degree bank angle. So anyway, so that's just kind of something that is maybe a little bit counterintuitive but interesting that comes out of these equations. One other thing that you need to be careful about is that we've come up with these values here assuming this linear system. Okay, we've assumed everything here is within the assumptions of linear aerodynamics. Well, it turns out that that control, so let's look at, for example, delta A, and we'll put like 10 degrees, 20 degrees, and 30 degrees, and then the rolling moment that we would get from that. Okay, for small deflections from 0 to 10 or so, that's pretty linear. But then past that, we actually lose some effectiveness, and that's not exactly linear anymore. So in this analysis, we've assumed that this is linear. So the values that we're going to get out of this solution are assuming that linear relationship. That's okay as long as we know the mapping. So this delta A sat, for example, that we've got right here, as long as we treat that as some mapping back to a real aileron deflection that is not necessarily a linear relationship. So for example, if geometrically we can go out to 30 degrees here, this is the maximum rolling moment that we could get. But with this analysis, we might say that our saturation angle is actually 20 degrees. And so we could run this analysis and say that that's equivalent to 20 degrees linear deflection. So as long as you know this mapping here of what the geometric deflection maps back to some equivalent linear deflection, you can still use this analysis to compute the minimum control airspeed. Okay, so yeah, I think hopefully this has been helpful to understand minimum control airspeed. And this again is the sizing case usually for multi-engine aircraft, and this analysis is how you could work through computing what that minimum control airspeed would be, and possibly how large your rudder needs to be, or your aileron, in order to trim out the aircraft for an engine out scenario. Now, one last thing I failed to mention is that we've got this square root sign in here when we're calculating the minimum control airspeed. And so you're thinking, well, that could be plus or minus. Well, as long as it's delta A over CW, we've got to use the same sign here as we do for the direction of our saturation angle. So if this is positive, the weight coefficient is always positive. So the sign of this is basically associated with the sign of deflection. And as long as we use the saturation angle in that same direction, then the signs here will always cancel. So they'll both be positive or both be negative, and so we'll always get out a real number for the minimum control airspeed.